In this video, I will show you how best to model the breaking and making of bonds between atoms. Through the use of a ramp, magnets, and marbles, my students and I have gotten a better grasp of how collisions may happen between chemical species, resulting in new atomic combinations. Let's picture the reaction between an alkali metal and water. Isn't it amazing how alkali metals can only stably exist when submerged in oil? But dunk it in water and you've got fireworks going off. Why is this reaction so spontaneous, in water no less, and even results in the appearance of a flame? From a quantitative perspective, why does the temperature increase when these two chemicals are combined? Besides the heat release, clearly a chemical reaction has taken place, as is evident from the hydrogen gas that can be captured, as demonstrated here by my student conducting a pop test. To explore the idea that the alkali metal, originally at room temp, and water, also originally at room temp, actually have a certain amount of kinetic energy that can be used to break existing bonds, which subsequently facilitates the formation of new bonds, I set up the following model for my students. It includes a ramp with a stabilizer, which I borrowed from my earth science colleague, who instead uses it to model water drainage and glacier movement. The metallic and non-metallic marbles, including a larger squeegee ball, represent the actual atoms or substances in the reaction. A neodymium magnet, which I taped underneath the ramp, serves as the bond maker with the metallic marble. I should note that this setup was inspired by the storyline called "Why Do Some Things Get Colder or Hotter When They React?" This is from the Next Gen Science Storylines and inquiryHub Chemistry. The actual student handout for this particular lesson involving the breaking of bonds is shown here with the links to the document as well as the key located in the description below. Also, check out my video that summarizes the first half of this exact storyline linked above. The next question to ask is, what is required for the breaking of a chemical bond? The marble in our model obviously needs a certain amount of kinetic energy, hence the 6 books stacked below the ramp. I counted them. To enable quantitative observations, I borrowed a speedometer from my physics colleague, which allows my students to measure the speed of a squeegee ball before and after collision with the metallic bonded marble to the magnet underneath the ramp. They then figured out the required minimum speed needed to break this bond. With, as I said earlier, 6 books, the squeegee ball reached a speed of 1.24 meters per second and was capable of releasing the metallic marble stuck in the middle of the ramp. But when the speedometer was placed just after the collision, this same squeegee ball rolled down the ramp at a reduced speed of 0.32 meters per second. Presumably, the reason the ball slowed down was a result of its collision with the metallic marble that is bonded to the magnet. Some of the ball's kinetic energy was transferred to realize the breaking of this connection and also provided the speed to the metallic marble as it rolled down the ramp. But what about modeling the making of bonds between atoms? Can we use the same or maybe a similar setup? Hey, why not? We sure can. This follows lesson 9 of the storyline that I referred to earlier. And again, you've got the lesson handout and the key located in the description below. All right, back to the ramp and the magnet marble setup. So the magnets can now actually be placed underneath because the ramp can now be flat, horizontal, right on the lab bench. No books needed. So the red squeegee ball is placed right above the magnet underneath the ramp. The metallic marble is positioned really close to that red squeegee ball, close enough for the magnet to pull it in. And as you can see here, when that collision happens, boom, the red squeegee ball goes straight to the other side. So, what is the effect of magnet strength and kinetic energy released upon bond formation? Well, we tested it out. If you use ever-increasing number of magnets, would that actually result in an ever-increasing speed that the red squeegee ball would have when it goes through that speedometer? So I'm showing you actually some data of 3 different sets of tests using either 2, 3, or 4 magnets, or none, and it shows you that exact relationship. The more magnets you have in your system, the greater the kinetic energy released upon the making of that bond. Important concept. So that actually brings me to one of the other lessons within this storyline that basically involves the question, do all chemical bonds have the same strength? Just like, do all magnets have the same magnetic strength? Check out the video linked above that details how dissolving these various kinds of salts either causes the temperature to increase or decrease, evident from different kinds of bond strengths that hold the ions that make up these salts together. All right, let's connect this setup to the reaction between potassium and water again. Okay, so when we look at potassium atoms and the atoms inside water, the oxygen and hydrogen, it certainly takes an amount of kinetic energy to break these bonds, as shown here with the small flames. Once those bonds are broken, new combinations can reappear. So potassium now chooses to hook up with hydroxide, and the remaining hydrogen atoms combine together to form the hydrogen gas. And a result of these new combinations, a lot more energy is released. So weaker bonds were broken, stronger bonds were formed, and therefore we have an exothermic reaction happening. So that realization is so key for the students. And to show this in a more general way, if we start off with a very simple set of molecules, diatomic molecules in this case, if it takes less energy to break the original bonds and more energy is released when new bonds are formed, that means it's an exothermic reaction. Alternatively, if it takes more energy to break the original bonds than is released when new bonds are formed, an endothermic reaction takes place, and the environment feels colder. Again, this was inspired by storyline. Why do some things get colder or hotter when they react? Stay tuned for the second half of this storyline, because the video that I've released earlier only shows you the first half of this entire set of lessons. The standards that this lesson relates to comes from the Next Generation Science Standards, or the equivalent New York Science Learning Standards, and it all revolves around matter and its interactions. So thank you for watching, bedankt voor het kijken, and see you in the next video.